Hello all. So in the last session we were talking about what is dimensionality reduction, how does that help in improving the performance of the model, and then we've also seen one problem that comes with dimensionality reduction, which is curse of dimensionality, right? So today in the session I would like to talk about another important dimensionality reduction technique, which is principal component analysis. Okay. So let's see what is principal component analysis. Basically, when I talk about dimensionality reduction, we have seen if there are more number of input features in a data set which are not contributing to the overall performance of the data set, we usually tend to remove them. But in the process of removing or reducing the number of features, it actually affects the accuracy of the model. So principal component analysis will balance between the accuracy and the model performance. So without disturbing the accuracy of the model, we'll try to reduce the number of features by using principal component analysis. So let's clearly understand what is principal component analysis. As you can see, principal component is basically a dimensionality reduction or a machine learning method, dimensional reduction technique or a machine learning method which will actually simplify the larger data set into smaller set while maintaining the significant patterns or trends. That is, without disturbing the information or without losing the information in the data set, we will actually try to reduce the data set such that it does not affect the performance. Okay. Now when I talk about reducing the number of variables in a data set, that naturally comes to the expense of accuracy. But the trick here in the dimensionality reduction is to have the trade-off between the accuracy and the performance. Okay, because usually when we go for smaller data sets, they're easier to explore, they're easier to visualize, they're easier to analyze the data points, much easy for faster or machine learning algorithm, but we may not get good accuracy. Okay, so to sum up, the idea of PCA is very simple: to reduce the number of variables in the data set without disturbing the performance of the model. Okay, now let's see how do we do the principal component analysis. Okay, so there are 5 important steps that we have to understand when we talk about principal component analysis. First, let me explain you all the 5 steps on how do we do PCA, and then we'll see how PCA is actually important with visualizations. Okay, now when I talk about principal component analysis, as you can see, there are 5 important steps. First is we have to standardize the values in the data set. Okay, often when we look into a data set, we have 5 different features. For example, when I talk about house price prediction, okay, so the house price is predicted based on the SFT. Okay, now how are the square feet values given? The minimum square foot would be around 600 to 700 and the maximum square foot would be around 2000 or 3000. Okay, so when I talk about the data set, okay, so the values in the square foot are usually higher. Okay, when I take the next feature as the number of bedrooms, which we consider for house price prediction, the number of bedrooms would be around 2 to 5. Okay, not more than that. So the values for the house price are ranging high, whereas the number of bedrooms, the numbers given for that would be very low. So in order to avoid this discrepancy in the scaling of the values, we usually go for standardization, which would be the first step. After that, we would like to compute the variance, that is the covariance between the values, such that we will identify the correlation between each feature. Understanding the correlation actually gives us importance about what feature has to be included and what feature has to be discarded. Okay, after that we compute the eigenvalues and eigenvectors of the covariance matrix and identify the principal components. So when I talk about PCA, identifying the eigenvalues or eigenvectors will actually help us understanding the principal components which are required for our analysis. Once we are done with that, we'll create a feature vector which will actually decide which PCA to keep, because we are trying to calculate n number of principal components, and once we are done with that, the feature vector will actually gives us which principal components have to be included and which has to be discarded. And finally, we'll have the recast of the entire data along with the principal component axis. Okay, so these are the 5 steps that we actually use for finding principal component analysis, and let us discuss about each point in detail. Okay, so as I told you, standardization helps us in understanding the range of values and standardize the values such that there would be no discrepancy in the machine understanding about the data. Okay, so if you have large differences in the ranges of initial values, they will dominate over the small values, and the machine will have discrepancy in understanding which has to be given importance. So they'll have biased results. Okay, so transforming the data to comparable scales can actually prevent the problem. So mathematically, for standardization, we subtract the mean and divide by that the standard deviation, the original value minus mean by the standard deviation. Okay, so once the standardization is done, all the variables would be transformed to the same scale. Okay, so this is the importance of standardization. So once we are done with standardization, as you can see, in the next step we will go for computing the covariance of the matrix. Okay, when I talk about computing the covariance of the matrix, it is very important to understand that we have to understand how the variables of the input data are varying from the mean and with respect to each other. Okay, so when I talk about mean is nothing but the average value. So if suppose I have 10 data points, okay, so we have to understand how each data point is deviated from the mean and how each data point deviated from each other. So to understand this, we actually go for covariance. Okay, so the main aim of this particular step to understand how the variables of the input data set are varying from mean and are varying from each other. That is, we are simply trying to find out the relation between each variable. Okay, so for calculating the covariance, we create the covariance matrix of n by n, let's say p by p here. Okay, p represents the number of dimensions. Okay, now for example, if you go for a 3-dimensional data with 3 variables x, y, z, the covariance matrix would be given in that way, calculating covariance of x with x with y, x with z. Next y with x, y with y, y with z, and then covariance of z with x, z with y, and z with z. Okay, so this is for 3D matrix. Similarly, we'll do it for 2D matrix as well. Okay, now since the covariance of a variable with itself is its variance. Okay, when I talk about covariance of a comma a, that would be variance of a. Okay, so that would be in the main diagonal. Okay, so we actually have the variances of each initial variable, and since the covariance is commutative, that is covariance of a comma b is equal to covariance of b comma a. Okay, so all the entries of the covariance matrix are symmetric with respect to the main diagonal when you plot it. Okay, so which means that the upper and lower triangular portions are actually equal when you calculate this particular covariance matrix. Okay, now let's see what do the covariances that we have as entries of the matrix tell us about the correlation. Okay, when we were talking about that, we say that by calculating covariance we have the relation between the variables to be found out. Okay, now when I talk about the relation and calculating the covariance, okay, so it actually says if the covariance value is positive, then we say the two variables increase or decrease together, that is they are correlated. If you have negative values in the matrix, that say if one increases the other decreases, that is inversely correlated, they are correlated in the reverse way. Okay, now that we have the covariance matrix, okay, so this is not enough actually to summarize the correlations, we should also go for the next step. So in the next step we actually compute the eigenvalues and the eigenvectors. Okay, so we try to compute eigenvalues and eigenvectors of the covariance matrix to identify the principal components. Okay, so we know how to identify. I'm not going to explain you this in depth, we just have to go through the 5 steps briefly. Okay, so first we calculate eigenvalues and eigenvectors, which are nothing but the linear algebra components that we use to compute from the covariance matrix and define the principal components of the data. Okay, now what we actually have to do is, first you need to know about eigenvalues, eigenvectors. Okay, so they always comes in pairs, right? So that every eigenvector has an eigenvalue, also their number is equal to the number of dimensions of the data. This is very important, please try to understand this. For example, when I talk about a 3-dimensional data set, there are 3 variables x, y, z, therefore there are 3 eigenvectors with 3 corresponding eigenvalue pairs. Okay, that is 3 eigenvector and eigenvalue pair. Okay, so it is eigenvectors and eigenvalues who are actually behind all the magic of principal components, because the eigenvectors of the covariance matrix are actually the directions of the axis where there is the most variance, that is the most information, and that data is called as principal components. Okay. As you can see in this example, let us consider a two-dimensional data with x and y. Okay. So once we calculate the covariance variable, we will calculate the eigenvectors and eigenvalues of the covariance matrix, and we try to generate the lambda value. Okay. If we rank the eigenvalues in descending order, you can see that lambda 1 is greater than lambda 2, which means that the eigenvector that corresponds to PCA1, that is V1, and the one that correspond to the second principal component PC2, that is V2. Okay. So V1 is greater than V2. Okay. So after having all these principal components, okay, so we compute the percentage of variance, that is the information accounted by each component, and hence we divide the eigenvalue of each component by the sum of eigenvalues. So when we apply that, we will understand how each one of them are contributing. Okay. Now once we are done with calculating eigenvalues and eigenvectors, we try to create a feature vector. Okay. So as we saw in the previous step, we have computed them, and now we will allow, and we will that step allows us to find the principal components in order of significance. Okay. So what we do in this step is we will decide whether to keep these components or discard those with lesser significance or lesser eigenvalues or low eigenvalues. Okay, with the remaining things, we will find the matrix of vectors that we call as feature vector. Okay, so the feature vector is, simply understand that the feature vector is nothing but a matrix that has columns, the eigenvectors of the components that we decide to keep, which will make the first step towards dimensionality reduction, because if we choose to keep only p eigenvectors, okay, out of n, the final data set will have only p dimensions. Okay. So once we are done with selecting the components, we will recast the data along the principal component axis. Okay. So apart from standardization, you do not make any changes in the data. You just have to select the principal components from the given feature vector in the fourth step. Okay. And then carry on with recasting the data. Okay. Let's quickly analyze those 5 steps. First we calculate, see, I have x1, x2, x3, x4 to xn as my values, input values. So I'll calculate my mean first. After that, I'll try to compute the covariance matrix with respect to the mean that I've calculated, and then I'll calculate the eigenvalues and eigenvectors. Okay. So first I'll calculate x mean, and then I'll calculate the covariance matrix with respect to mean, and then with respect to this covariance matrix, I'll try to calculate the eigenvalues and eigenvectors for 0 to n minus 1. Okay, in third step. And fourth step, in order to minimize the dimension of the given features, I'll try to choose only the ones which are contributing. So I'll try to minimize the feature vector. Okay, FV stands for feature vector, and then finally I'll have the new feature vector which is computed based on the above calculations. Okay, so these are the 5 steps with which we understand about the principal component analysis. Okay, now when we talk about what are principal components, okay, so just understand that principal components are nothing but the new variables which are constructed as linear combinations of the initial variables. Okay, now these combinations are chosen in such a way that the uncorrelated or most of the information of the initial variables are squeezed or compressed. Okay, so the idea is, if you have 10 dimensional data gives you 10 principal components, we have to reduce them to only minimum which will actually contain the original information. Okay, so geometrically speaking, principal components are nothing but, they represent the directions of the data, okay, with maximal count of variation. Okay, to put all this simply, I just can say that, just think of principal components as new axis that will actually provides the best angle to see and evaluate the data, so that the difference between the observations are better visible. Okay, now how PCA constructs the principal components. Okay, so there are many principal components as there are variables in the data. Okay, so principal components are actually constructed in such a manner that the first principal components accounts for the largest possible variance. Okay, and then the other principal components will have gradually reduced variance. Okay, as you can see in this particular diagram, let's assume the scatter plot of a data set. Okay, now we can guess the first principal component, right? Yes. Okay, it's approximately the line that matches the purple, because it goes through the origin and it's the line in which the projection of the points, that is the red dots you can see, which is most spread out. Okay, so mathematically it's the line that maximizes the variance. Okay, maximizes the variance. Okay. Now the second principle, how about the second principle? The second principal component is calculated in the same way, but with the condition that it is uncorrelated. Okay. Uncorrelated to what? Uncorrelated with the first principal components, and that it accounts for the next highest variance. This continues until you find the total number of principal components that have been calculated, which is equal to the original number of variables. Okay. So as you can see in the 2D example, okay, consider the data set with two dimensions like height and weight, height versus weight. Okay. So the data set can be plotted as points in a plane. Okay. But if you want to tease out variation, that is PCA will find the new coordinate system, as you can see on the second figure, okay, on the right hand side. The axes don't usually mean anything physical, they are just the combinations of height and weights called principal components that are chosen to give the axis lots of variation. Okay, so you can also have another example of 3D here. Okay, as you can clearly see, with 3 dimensions PCA can be more useful. It's hard to see through a cloud of data. Okay, in the example below, the original data are plotted in 3D, but you can have the projection of the data into 2D through a transformation, as you can see. Okay, to see the official PCA information, you can just click on that. Okay, so the top figure is without PCA, the bottom figure is with PCA. As you can see, the principal component is applied, and we have 3 different on the middle, second side on the third figure. Okay, so you can see 3 different groups of the data and how the PCA is actually applied onto this particular 3D data. Okay, so the vertical axis PC2, the second most, and the third axis PC3, the least. Obviously PC3 is the one that we drop because it has the less axis here. Okay, the more axis and the less axis, so we'll try to drop PC3 after applying the PCA. Okay, so this is before PCA and this is the one which is after PCA. Okay, so this is all about principal component analysis. Basically understand, principal component analysis is also one of the data reduction techniques which will reduce the number of features, balancing between the accuracy and the number of features, complexity in short. Thank you.